Flat earthers tend to use very strict and narrow definitions of experiments and the scientific method. It should come as no surprise that this is due to a complete lack of understanding. The scientific method is really simple and rather intuitive if you think about it. It's a cyclical process that goes through observing something or asking a question. This then forms the basis of our hypothesis. We then test the hypothesis by doing things in a systematic way and then analyzing the outcome so we can draw a conclusion. The big thing that I want to point out is that this is a cyclical process, and by design it is vague. The reason for highlighting this is that a lot of the flat earth pseudoscience peddlers will take a very strict definition and usually treat it as a linear process where you must start with the observation of a natural phenomenon. They then conclude that if you deviate from this, then your investigation does not follow the scientific method. The big problem is that this excludes any investigation which starts with a simple phrase of, well, fuck it, let's see what happens when we press that button. The rules are vague because of the wide application. Whether you study physics or paleontology, you have to use the scientific method. However, to approach an investigation in these different disciplines in the exact same way is just silly. Scientists also rarely spend their days thinking explicitly about how their approach conforms to the scientific method, and this is because it is just second nature. Now, and as a result, it may appear like a researcher employs a slightly different version of the scientific method, but when you break it down, the same series of steps will fall out. But let's have a look at the steps. A good starting point is the observation or question stage. Now, the flat earth requirement that there must be an observation of a natural phenomenon is about as useful as a marzipan dildo. It excludes that possibility that there may just be something in the theory that's worth exploring, something we haven't observed, but what the theories or logic predict. A great example of this is gravitational waves. At no point did we observe them, but we concluded that if our understanding of general relativity is correct, then we would expect gravitational waves to be a thing. The same thing happened with black holes, the particles described by the Standard Model, or elements in the periodic table. So in this sense, our observations are predictions made by our theories. Alternatively, we could take conclusions from other studies. For example, we can take a study that shows that meat consumption is lower in rural China, and another study that shows that the incidence of cancer is also lower in rural China. We can then raise the question as to whether meat causes cancer, and then fail to publish on the study and forced to write a popular science book where you can peddle your nonsense to the masses. In case you've missed this, this is a reference to a book called The China Study, which is a load of unadulterated horseshit. But once we have an observation or a question, we can form a hypothesis. A hypothesis is essentially a simple statement which can be evaluated as true or false, or when you delve into the nitty-gritty, you most commonly come up with, well, maybe, at which point you have to rethink your approach. But forming a hypothesis can be as simple as just reframing your question into one of these statements. But there are other ways to go about it as well. In physics, we are now in a position where our theories are not always described by a series of simple equations which we can easily rearrange to form a simple hypothesis. We often come across equations like this one, and I'll give you a few seconds to figure out why this equation is so damn difficult. Now, don't worry if you haven't spotted it, but this equation is called the Landau-Lifshitz-Gilbert equation, which describes the magnetization of a single spin in a magnetic field. The problem is that we have independent variables h and m and a dependent variable dm by dt, which is also an independent variable. To add complexity, we also have to consider the magnetic field caused by the spin, which is adjacent to the spin, and take into account that we are trying to solve for 500,000 spins at the same time. The result is that we can't actually solve this analytically, and we have to do it numerically, and for this we employ simulations. Now, when doing simulations, we also follow the scientific method. We start with an educated guess based on known results and build a hypothesis along the lines of, well, according to my understanding of the theory, this should happen. When we run the simulations, we get lots of data back, and we can use this data to figure out a relationship between different quantities. Our simulated experiments are then a test of how well our predictions match scientific theory. Provided that all the simulations were performed correctly and a hypothesis evaluates the truth, then your hypothesis is consistent with scientific theory, and this conclusion will then become the hypothesis of the main experiment. And this is the domain in which computational and theoretical physics lives. There are many ideas in physics around areas such as dark matter or dark energy, which are a result of these kinds of investigations. However, these ideas are still hypothetical. Many people, myself included, have published on this process alone, but the key point is that this process generates hypotheses only, and these are to form the basis of further real-world experiments. But now we've established a hypothesis, we can test it. The next stage is often referred to as the experiment stage. However, this is a misnomer, as an experiment has a very strict definition. An experiment is a method where researchers manipulate an independent variable and observe a change in dependent variables whilst controlling for other variables. However, there are more ways in which you can investigate a relationship between the IV and the DV. We can also do field experiments, randomized controlled trials, quasi-experiments, cross-sectional studies, longitudinal studies, case control studies, or combinations of these, but I will cover them in another video. If we take the classic controlled experiment where the experimenter has full control over everything, then the test stage is relatively simple. Note my use of the word relatively. Throughout your experiment, you will have to do acceptance testing and calibration for every bit of equipment that you use. Here, you check that everything works as expected and make sure that you know how it behaves. This could be as simple as making sure that your scales actually give you an accurate reading of mass, or that your electromagnet actually produces the magnetic field that you expect. Each of these steps are mini investigations in themselves, and they have to follow the scientific method. Fortunately, these tests are usually quite simple, but in some cases they are not. There is an entire field of physics dedicated to developing tools to perform experiments, and many PhD students will have spent a significant amount of time building their own apparatus for measuring things. Once you have tested all the individual bits, you are still not done, however. You have to test whether the whole ensemble actually works as expected. And guess what? This involves a whole scientific investigation in itself. But once you think that you have all the data that you're after, you can go to the analysis stage. Simply put, this is the stage where we see if the results match the predictions. Now let's take this equation. And we have this data set. We can then fit this equation to that data set. Now, this in itself is also a scientific investigation and is an experiment in itself, where you hypothesize that the model fits the data and you test the fit. Your independent variables in this are the fitting parameters, A and lambda in the case of this model, and your dependent variable is an objective measurement of how good your fit is. And you will notice that values for A and lambda popped up on the screen along with some errors, and these are useful because these values could represent values which are known, such that we could use them to check our work, or these values could form the subject for further studies. Your conclusions could be as simple as that the model does fit or it doesn't, and on that basis you either accept or reject the hypothesis, or more formally you either reject or accept the null hypothesis. But now you have drawn a conclusion, you can use this to form the basis of the observations for your next go around the cycle. But before you do that, you write everything up and send it off to a journal, or just print it off and throw it into the forest so you can tell your colleagues that you have submitted to Nature. Flat earthers tend to use a really narrow definition of what the scientific method is and what it entails, and it gets portrayed as a simple linear step-by-step process with very strict definitions of what can happen at each step. In reality, the scientific method is very loosely defined and a circular process. Because of this, there is the possibility of infinite complexity. Whereas you may have been taught that the scientific method looks like this, you'll very quickly realize that this is just a fundamental building block. In reality, when you're trying to describe your investigation using this building block, it looks more like this. And this is why it took 12,000 scientists, $13 billion and 35 years to detect the Higgs boson. If you can give a full and exhaustive description of your investigation and it only follows this, then you can be pretty damn sure that your investigation was not done properly.